So, welcome everyone to the last section of the day. It's an absolute pleasure to have Yuval Desai. I will talk to us about low complexity cryptography and simple hard to learn functions. Yuval, take it away.
Hi, can you hear me?
Yeah, I do. Yeah.
Okay, thanks. Yeah, it's a pleasure to be here, at least virtually. Unfortunately, I couldn't make it, but I will be in Berkeley on Thursday and Friday. So if anyone wants to talk about any of these topics or anything else, I'm happy to meet. Great. So this will be a fairly broad survey style talk. I will start by giving some historical perspective on connections between, and the basic connections between cryptography and learning, focusing mainly on connections between low complexity cryptography and the hardness of learning simple functions, as the title of the talk suggests. Then I'll zoom out a bit and talk more generally about the area of low complexity cryptography, some of the challenges involving assumptions and open problems in the area. And I will conclude by talking about a recent line of work that proposes and analyzes new candidate pseudorandom functions in very low complexity classes. Okay, so please feel free to interrupt me with questions. And as I said, I'll be happy to talk later this week with anyone who's around. Okay, so a very quick crash course on cryptography. So traditionally, crypto was about securing communication, but nowadays we tend to be much more imperialistic, and we view cryptography as pretty much anything that can be phrased as allow good guys to realize some goal G while preventing bad guys from interfering in some way B. Here, the cast of characters, the basic cryptographic primitives I will refer to in the talk. We already heard about them in previous talks, so I'll be very quick. In one-way functions, the good guys want to efficiently compute F, and bad guys should be unable to invert F on a random input if they're computationally bounded. A PRG stretches a short seed S to a longer output Y such that bad guys cannot distinguish between the output on a uniformly random seed and a uniformly random Y. And finally, the most important primitive for the purpose of this talk is a pseudorandom function. It's a function that takes a secret key K and a public input X and outputs a public output Y. And the security property is that bad guys, even if they have Oracle access to the function, they cannot distinguish between the case where they interact with the real function with a uniformly random key and interacting with a totally random function with the same input and output length. And whenever I refer to, say, a PRF having a hardness T or security level T, T is a bound on the number of queries to this oracle, and the running time can be polynomial in T. So I will refer to things like quasi-polynomial security, sub-exponential security, exponential security in the natural way. There's also a weak version of a pseudorandom function that was also mentioned by Benny earlier today, where security is only required to hold with respect to uniformly random inputs. Okay, we'll also consider a few higher level primitives. Very briefly, encryption enables good guys to transmit the message via ciphertext C such that bad guys cannot learn the message from the ciphertext, and it comes in a secret key flavor and a public key flavor, where in the public key flavor, encryption only uses the public key. There is a signature scheme and its private key version, which is called the MAC, a message authentication code, where the goal is to protect the integrity of a message M by attaching some tag sigma. And the goal of the bad guys is to make the verifier or receiver accept the wrong message M. And finally, in secure computation, we have two or more parties who want to compute some function F on their secret inputs. And even if some of these parties are bad, they should not learn any information in a computational sense about the inputs of the other parties from the messages they receive. Okay, so these are cryptographic primitives I will refer to in the talk. and I assume that most of you are already familiar with them. Okay, so let's get back to when it all started. This is how my laptop used to look like in these days. Fortunately, we didn't have to give virtual talks because there was no COVID. So in a pioneering work of Valiant, introduced the notion of PAC learning. This model, and everything I say throughout this talk, only requires improper learning in the sense that the hypothesis output by the learning algorithm does not need to come from the same class as the function or concept being learned. It's distribution free by default in the sense that it should work for any input distribution. And finally, it should guarantee approximate correctness with respect to the input distribution. So the hypothesis that is output by the algorithm should be correct with high probability on an input chosen from the right distribution on which it is trained. And already back then, Valiant observed that negative results on learning are implied by cryptography. He says there is circumstantial evidence from cryptography that the whole class of functions computable by polynomial size circuits is not learnable. He provides a laconic justification, which is quite informal, especially because at the time there was not sufficiently good formalism to be able to state such a conclusion based on a clean and nice assumption. And this was taken care of in another pioneering work by Goldbach et al., who introduced the notion of a pseudorandom functions that I defined before. The main result is a construction of a pseudorandom function from any one-way function. And an application was a hardness of learning under a nice assumption. So quoting the paper, they say one may conjecture that all functions f that are simple can be approximately inferred after temporary access to an oracle for f. We show that this is not the case under the assumption that one-way functions exist. So this is great because one-way functions are implied by many assumptions, by many concrete and widely acceptable assumptions that people had even back then. One should also note that, in fact, a pseudorandom function rules out even a very, it gives a very strong hardness of learning result because it applies even to learning algorithms that can make membership queries. Even if we only restrict learning to a specific high entropy input distribution and even if we only settle for a weak approximation guarantee where we have to predict the function with slight advantage over guessing. So PRFs gives us a very super strong hardness of learning result, and even a weak PRF gives us a strong hardness of learning result, which is hardness of PAC learning even under the natural uniform distribution. Okay, so these are all nice consequences of basing pseudorandom functions on nice assumptions. The next paper by Kearns and Valiant says the following. So great, we know that under nice assumption, some functions cannot be learned, but what about shallow functions that have a shallow circuit, say in the class NC1 or even TC0? Can we establish hardness of learning for such functions? And one obstacle is that the GGM construction of pseudorandom function did not respect the parallel complexity. So even if we started with a super parallel one-way function, it would not give us a parallel PRF. And they took a different route, which is similar to what Andre started with his talk with, and they said that a decryption function of a public key encryption scheme has to be hard to learn because otherwise we can infer a decryption of a new fresh ciphertext from a training sample that we can generate using the public key. And the main technical contribution was showing that we can build encryption schemes where decryption is in low complexity classes such as NC1 or TC0. So this was very satisfying and already got us something which is very low in the complexity hierarchy. But even they were not completely satisfied, and they say a technical open problem is to improve the constructions given here to even simpler classes of formula and circuits. And this was indeed this type of cryptographic hardness approach to show hardness of learning simple classes of function has been a topic of a lot of follow-up work, especially in the computation, in the COLT community. Okay, the final historical paper I will mention, this is another influential paper of Blum et al. That I will refer to as BFKL. We heard about it from Ayush as well. And here they say the following, why be so negative, right? Previous results took standard nice cryptographic assumptions and used them to show that we cannot do certain things, that we cannot efficiently learn. Why not turn the tables and make this into a positive thing, this connection, and use simple problems that we conjecture to be hard to learn towards building simple and efficient cryptographic primitives. So their work mainly focuses on the learning parity with noise, LPN problem that we heard a lot about from Ayush. And the main technical result is the search to decision reduction that we also heard about from Ayush. Their motivation was to build a direct construction of a pseudo-random generator from the LPN assumption, which was previously built indirectly in an inefficient way by Goldratt, Kravchuk, and Luby by using just the one-wayness of the noisy encoding problem. So this was their motivation for looking at the LPN assumption. Something that perhaps less people know about, certainly less cryptographers know about, is this short subsection in the paper that proposes a simple weak PRF candidate, which is so simple that it can be computed by polynomial-sized DNF. This is even lower than the class of depth-3 things that Benny talked about. And the function is really simple to describe. The secret key consists of two secret sets A and B of input bits of logarithmic size. And the function outputs the parity of the input bits in A XORed with the majority of the input bits in B. Okay, that's, they just put this as a conjecture. This is a weak PRF. It's certainly simple, it's low complexity. That's fantastic. And quoting them, they say, as simple functions continue to elude efficient learning, blah, blah, we can exploit this intractability to obtain simpler cryptographic primitives. So they really put forward an agenda of using conjectures from learning, hardness of learning towards better cryptography. Now, okay, let's look at their conjecture. The natural reaction is, wait a minute, aren't they assuming the problem away? Where's the math, right? So this seems like something that we're not trained to do. And if we read their explanation, they say the following, this is a distribution on DNF formulas that seems to defy all known methods of attack, and we believe that any method that could even weakly predict such functions over a uniform D would require profoundly new ideas. Okay, so first of all, just reading this, they sound like people who know what they're talking about. And maybe they were lucky, but more likely what they say was actually based on a lot of math, but they just didn't bother including it in the paper. So basically, based on a lot of gained experience for the time, they made such a statement. You know, it survived the test of time. Today we know a lot more about related problems such as learning juntas and so on. But I guess that the same sentence could have been written today in the exact same words and totally stands the test of time. Okay, nice. So now, suppose that we accept this assumption, aren't we done, right? Doesn't this give us the best possible result, the PRF by DNF, right? You can't go lower than DNF. Okay, and NC0 is not a class where you have pseudo-random functions. Well, there are several problems with this. First, it's only a weak PRF. Ideally, we'd like strong PRFs. More importantly, it only gives us quasi-polynomial hardness, okay, which in many cases, certainly for crypto applications, also for natural proof applications, this is considered to be insufficient or borderline easy. So in fact, both limitations are inherent not only to DNF, but also to AC0 as shown by Lineal et al. But something else about this assumption, which perhaps explains why it hasn't been more popular, at least in cryptography, is that it really hasn't found any interesting applications as far as I know. Maybe in part because of lack of awareness, but trying to think about it, I could not find any natural application. Now, we could go beyond quasi-poly hardness by increasing the size of the sets A and B, but this would put us in the class TC0, for which we have strong PRFs under standard assumptions, so there is little motivation of doing that. Okay, any questions up to this point? I'm not sure I can see the chat. Okay, now I can see the chat. Okay, cool. So let me continue.
Yeah, there is one actually.
Yeah. There is a question?
Yuval, Ayush this side. So my question was, when you say quasi-polynomial hardness, is this about the size of the adversary, or is it about the distinguishing advantage, or both?
Right, so it's both, right? So the adversary can generate quasi-poly many samples and then use quasi-poly time or circuit size to distinguish. Yeah, thanks.
Does it also hold if the number of queries are limited by a polynomial?
No, so if the queries, as in Benny's talk, if the number of queries is limited as polynomial, then we can get potentially better hardness. Yeah, that's a good point. There is still an empirical correlation. So things that are only quasi-poly hard in this sense will typically have worse concrete parameters, even when you consider a smaller number of samples, but there is no formal justification for that claim. Okay, so let me try to recap and a bit look forward to the rest of the talk. So we have this two-way connection between crypto and hardness of learning. I will focus from here on. So if we have a simple PRFs, they always give us very strong hardness of learning results about simple functions. The converse direction is less general. Even just for quantifier reasons, for instance, we can get hardness like Danieli et al. Obtained, hardness of learning results from average case Feige-style assumptions that Ayush also mentioned. But morally, most natural instances of hard to learn functions do imply some kind of PRFs. So we have this two-way connection, but in the rest of the talk, we will mostly forget about the learning part and focus on the questions of constructing simple PRFs, mainly because they also serve as a hub for other applications. For instance, in complexity theory, we can get natural proof barriers, which is a negative result, but still something that can save a lot of time for the community. And in crypto, we get quite a growing number of applications based on simple PRFs. I should note that there are many different notions of simplicity. This is part of what makes this research area so rich, is that each community and each application domain has its own notion of simplicity. So I will not talk, for instance, here about notions of simplicity that involve computations over the reals or geometric concepts and so on, but these, of course, arise in many domains of statistical inference and learning. And one thing that kind of makes the cryptographic applications stand out is that they create a real market for simple, hard-to-learn functions. Again, it relates to this positive aspect of the application that I mentioned before. And it's literally a market because, we use cryptography and specifically primitives that can be based on PRFs, like symmetric private key encryption or authentication. We use them to protect our money, to protect our sensitive data. So simplicity is a virtue. Now, you may ask whether the PRFs that are used in practice are simple. Well, one reason, so things like AES, one reason why they're not simple in the traditional theory sense is that they have to implement something stronger than a PRF. It's a pseudo-random permutation, which needs to be also efficiently inverted. So this is one reason why they are not simple in the sense I will talk about later. But something else that actually gives us a very, very strong motivation for simplicity in the theory sense is a growing number of applications, or practical applications, where we want to evaluate the PRF by a secure protocol, which distributes the evaluation of the PRF between two or more parties. So we split the key and the input between two or more parties because we want to eliminate a single point of failure. And now the parties should engage in some secure computation protocol to learn the value of the function for the purpose of signing or for the purpose of encrypting. And when considering this distributed setting, then the notions of simplicity that we need are much, much more restrictive, less tolerant than silicon, you know. And in fact, yes, so in fact, I'll talk about it later in the talk, but there are some very practical applications for notions of simplicity that usually we talk about only in theory. And this applies not only to secure computation, but to also to other advanced crypto primitives, like we can talk about FHE-friendly PRF, ZK-friendly PRF, maybe in the future when IO becomes practical, IO-friendly PRF. And there are very good reasons to consider these types of combinations, and each of them will typically define some relatively clean metric, which is very different from the metrics that people typically consider when designing block ciphers. Okay, question. Any no implication of, say, weak PRF in low complexity classes to the existence of public key encryption scheme? Great question. I don't know of any such general relation. A long time ago, when working with Benny and Eyal on the questions of crypto in NC0, we were kind of hoping that you can show that LPN is implied, some low noise version of LPN, and this via Lechnovitz construction can get public key crypto, but we didn't succeed in pursuing this agenda. Okay, great. So to give you some teasers, some example of a challenge problem in this domain, let's consider the goal of an asymptotically optimal PRF. This is, you can think of it as some kind of a holy grail of, from an asymptotic point of view, of symmetric cryptography. Or from a learning perspective, you can think of a function that is maximally hard to learn. Namely, we cannot even get a super polynomial speedup over the naive algorithm, and at the same time is maximally easy to compute in the bounded fan-in Boolean circuit model. Okay, so this is a notion of asymptotically optimal PRFs, and you can think of this question, you know, using the provable approach of Kearns and Valiant. Can we base it under some assumption that we like? And this seems like a tall order. So maybe we can settle for a second best alternative of proposing a heuristic construction for such a PRF. And even this is surprisingly challenging if you think about it first. You might think, hey, let's just pick a random circuit. So first of all, if you look at existing designs of block ciphers like AES, like practical private encryption schemes, and you generalize them to an asymptotic construction, their complexity circuit size will be n log n. So it will be quasi-linear, but not quite linear. And if you think of a circuit, like a typical way to think of a circuit is as a rectangle. And if it has linear size and it's a rectangle, it has to have constant height, which means that we have constant locality, average locality, which means that it cannot be a PRF. So even just designing the topology of such a circuit is challenging. And it's not a coincidence because such a PRF from n bit to n bits, if you restrict it, say to, if you restrict it in an appropriate way, it's not hard to show that it implies linear time encodable codes, which are also quite challenging to design, even at the heuristic level. Okay, so that's a challenge, and we will get back to this challenge later. Okay, so this concludes yes, the first part. Let me switch to the second part, which is about low complexity cryptography. So this is an excellent research agenda. If you have students looking for research problems, there is an unbounded number of them. You can pick any crypto primitive. Here you have the cast of characters from the beginning of the talk, along with many others. And trust me, there are many more where this comes from. You can pick a target security level, even post-quantum to make things more interesting. Pick a complexity measure. We have many different complexity measures. Sometimes for distributed primitives, even communication and rounds, and now go as low as you can. Okay, this is a research agenda, that captures many problems which are only partially explored. Okay, so right. So what about assumptions, right? This is always an issue when discussing cryptography, sometimes also other domains like complexity theory or even math. Okay, what about assumptions? So the typical methodology that we like is to build the X under some acceptable assumption Y. What do I mean by acceptable? Well, it's a somewhat arbitrary notion. If you want a legal definition, then everything that can get your paper accepted is acceptable by definition. But in reality, it's more complex. So let's start with the basics. If there are no assumptions, then it's certainly acceptable. And in fact, we have a kind of a research area called information theoretic cryptography, which gets many types of results under no assumptions whatsoever. And to give just one historical example, that the whole study of PCPs started from asking a question in this domain, and in an interesting turn of events, it now leads to very practical zero-knowledge proof systems in the computational sense. Okay, so information theoretic cryptography has many applications, and we'll see also an example right now. But trying to draw the line between what's acceptable and what's not acceptable has been the topic of many debates and proposals. These are just a few of them. And typically we consider acceptable assumptions to be ones that are clean and succinct so that people can actually reason about them. We want them to be efficiently falsifiable in some well-defined sense. We want them to have an assumption to have several applications. We saw an example for that was the local PRGs as opposed to the BFKL assumption. We want them to have a win-win flavor, and we need them to withstand the test of time. Especially, we want a lot of relevant brain power to be invested in trying to break them. Okay, so these are all nice properties to have, but still, in reality, the notion of acceptable assumption, which we also call a standard assumption, is one that is used by those we trust. And it's heavily influenced by historical coincidences. Sometimes it depends on whether we can prove interesting theorems based on an assumption, and sometimes it just depends on who our friends are. Okay, so there is a lot of arbitrariness about the choice of assumptions, and indeed it's a moving target. So the question is, what if this methodology fails? What if we cannot base X on something that's considered acceptable? When is it okay to make new assumptions? Do we need to be certified? Do we need some special committee that will decide? Someone needs to be the first. And the theory community tends to be very conservative, and for very good reasons. So first, speculative new assumptions are often broken. We've seen this in the line of work on IO. before the final result that Ayush talked about. And also, perhaps not less importantly, the quest for minimizing assumptions gave rise to really a rich and deep theory that often had unexpected consequences and applications in other domains. Okay, so there's no doubt that being conservative is valuable, but what happens if we can't? So the alternative methodology is to do the following. Let's identify a class C, syntactically well-defined class C of natural constructions. Okay, let's identify a well-defined class A of natural attacks. And now let's try to find efficient construction from the class C that resists the attacks from A. Okay, so if we're lucky enough, and this often happens to be the case, this is a combinatorial problem with no inherent barriers, so we can hope to prove, unconditional results without encountering any P versus NP or similar open question. It gives us a systematic way for navigating what I call the crypto dark matter. It's anything that doesn't isn't a consequence of the standard assumptions. And it may and has in the past led to new acceptable assumptions. Okay, so this is an alternative methodology that coexists with the traditional methodology. It's very common, it's a must in applied crypto. However, there it's typically heuristic, so there are no rigorous proofs. It's not very systematic, and it's sometimes constrained by some arbitrary requirements, like have an absolute maximum level of security with no regard to efficiency. It's less common in theory-oriented crypto. We've heard a lot about these candidate constructions of local PRGs and one-way functions that originated from the work of Goldreich. And then more relevant to the current talk, there's been a similar line of work on pseudo-random functions. I don't count BFKL because they don't provide any formal justification, but works that introduced new candidates and provided serious analysis are Miles and Viola, Akavia et al., and others I will mention in the rest of the talk. Okay, so pictorially, this is the green, this is the whole space is the space of syntactically valid constructions of some crypto primitive. The green area are the constructions whose security is provable from acceptable or standard assumptions. Everything else is the dark matter. The red area are those constructions that are broken by natural attacks. And now the green area are all heuristic constructions that resist the natural attacks. The natural attacks ideally capture almost all the relevant attacks for the type that proved to work against candidates in a certain domain. And our goal here is to find the candidate construction in this green area that has the lowest complexity or is simplest in some sense. Okay, so let me now discuss concrete or basically a concrete metric for low complexity cryptography, and this is an important metric of circuit size. By default, we consider circuits of bounded fan-in, and here the goal is to minimize the asymptotic ratio of the circuit size required to solve a task securely versus the size required to solve it insecurely. Traditionally, this ratio grows with the level of security, and our goal here is to get crypto with constant overhead, namely this ratio is asymptotically bounded by an absolute constant. This sounds like a dream goal if you look at how traditional cryptography works, especially for advanced primitives like secure computation. Okay, so let's talk about a common building block in crypto and also in other areas, which is a universal hash function. And here I refer to the stronger notion of pairwise independent hash function. And so such a hash function takes an input X and the key K. And the pairwise independent requirement says that on any two distinct, if we fixed any pair of distinct inputs and pick the key at random, then the outputs will be uniformly random and independent. And by default, we consider H mapping n-bit input to an n-bit output. Okay, so can we build such hash functions by linear size circuits? Well, if you look at standard constructions, they all involve some non-trivial arithmetic, either finite field or polynomials, which require quasi-linear size circuits by known constructions. And this has led Mansour et al. To conjecture that actually n log n is the right answer. And about 13 years ago, with Kushilevitz, Ostrovsky, and Sahai, we refuted this conjecture and showed that such hash functions can be computed by linear size circuits. And let me show how. It's quite simple. So the construction has three phases. In the first phase, we apply a linear time or linear size encodable error correcting code to encode the n-bit input x into a code word over a larger but constant size alphabet that has, say, 90% minimal distance. So such an encoding is possible by combining, the linear time encodable codes, binary codes of Spielmann with a distance amplification, expander-based distance amplification technique of Alon et al. Okay, so now we have 90% distance. What do we do with it? Well, the second step is the only randomized step. Here, we take every constant size symbol and apply to it a real, like a perfect pairwise independent hash function with a fresh constant size key, right? It's constant size alphabet, so this is fine. So we're still within the complexity budget of linear size circuits. The final step, which seems more tricky to implement by linear size circuits, is to apply a transpose mapping of a linear time asymptotically good code, such as Spielmann's. So this, it's known by work of Shor et al. That this serves as an extractor for bit fixing sources, if this is a good code. And also there is a neat trick called the transposition principle, which shows that we can implement the transpose encoding with roughly the same circuit complexity as the original encoding. So overall, syntactically, we meet the linear size requirement. And as for pairwise independence, let's just illustrate proof by picture. So suppose we slightly change the input. We want to show that this makes the output totally random. So after the first step, we have 90% of differences with respect to the original input. After the second step, we have now 90% of entropy, and now this is extracted into a fully random output. Okay, so this is the construction. I should say that it's open to generalize it beyond constant. We can generalize it to constant k-wise independence, but it's open to get something beyond constant, proportionally scaling the output size. Okay, any questions about this construction? Yeah, how much time do I have?
I would say 6 more minutes, if that's okay. 6 seconds.
Yeah, sure. Okay, so back to coding theory. If we look at this family, if we instantiate this hash function, this H component by a linear function, a linear hash function, then we get the family of linear time encodable codes that have similar combinatorial properties to random codes. In particular, they meet the Gilbert-Vershamov bound with high probability, which is nice for coding, except that we don't know and we don't expect to have efficient decoding, but then we can turn it back and use it in cryptography and also in other applications as a linear time substitute for random linear code. So if you need a linear time substitute for random linear code in whatever application, you can consider using this kind of codes. Okay, so this is a table that briefly shows where we stand. So these are mainly results from the original paper about constant overhead cryptography, starting from no assumptions, which is universal hashing, or one-time MAC, which is just follows from pairwise independence, and culminating with a construction of constant overhead secure computation, where the parties are semi-honest, honest but curious, using a polynomial stretch local PRG. And interestingly, until today, we don't have any alternative route of getting this application except using, so there's nothing here that talks about, in the application, that talks about locality or polynomial stretch. And yet it's the only example I know of something that we only know how to do using local PRGs, and we don't have any alternative route, even a heuristic one. Okay, and there's a bunch of open questions. So we know how to do near threshold secret sharing with constant overhead, but sharp threshold, we don't know. There is recent progress on the exact circuit complexity, but it's restricted to polylog output size. And there's been a lot of progress on classifying other primitives. Let me just mention that this is a result that, again, built on this hash function and was used by Benny to show gap ETH hardness. He mentioned this in his talk. This is a new candidate that hopefully I will talk about very briefly in the remaining few minutes. That actually settles, if you believe our conjecture, then it settles this challenge of asymptotically optimal PRF, and it gives us, a natural proof barrier for linear size circuits, again, under this conjecture. And finally, we have open questions, zero knowledge, secure computation against malicious parties, which have been resolved for arithmetic circuits, but not for Boolean ones. Okay, so let me talk very briefly about new candidates for simple PRFs in very low complexity classes. I'm running out of time, so I will not, I will skip the background part. I will just say that we're interested here in better than quasi-polynomial security, which basically puts us outside of AC0. So there's interesting work that Benny mentioned on AC0 with quasi-polynomial security or better security if we allow polynomially many samples. But we're looking here for better complexity, at least sub-exponential. So the first class you might want to consider is AC0 on top of parities. This was a candidate proposed by Akavia et al. By depth3 AC0 circuit. So it takes a tribes function, it's a balanced DNF on top of random parities. And unfortunately, it was shown later by Bogdanov and Rosen to have a low rational degree, again, mentioned by Benny and Ayush, which gave rise to a quasi-polynomial time algebraic attack, which refuted the original conjecture. But fortunately, this is a recent work. We show that by adding 1 to the depth, we can get provable resistance to this rational degree attack, in addition to resistance to all the other attacks that Akavia et al. Proved resistance against. So this is where we stand in terms of AC0 on top of parities. It's a nice open question to consider PRFs, weak PRFs by AC0 on top of public parities. And it has some connection with the conjecture of Servideo-Viola that I will not have time to discuss. If we consider a different kind of AC0 circuits with parity gates, it turns out that we have candidates that actually, there's a really nice cryptographic motivation here and several applications. But let me focus on the candidate. If you take a certain kind of sparse polynomials applied to the key XOR with the input, this is a weak PRF with sub-exponential security under some natural variable density variant of the LPN assumption. We know that this class is path learnable in time 2 to the square root n. The thing for which we can get provable security is slightly worse, but we also have a conjectured candidate which matches this learning attack, like 2 to the square root n security, and it has different kinds of cryptographic applications. This is how the candidate looks like. I should just say that if you replace parities here by OR, then it's a DNF, and it's broken, easily broken in quasi-polynomial time, because you can just ignore the higher order terms. And the reason you can ignore the higher order terms in DNF is because the noise they add is one directional. Here you get this two directional noise, and then the more samples you have, the higher the degree of the terms that kick in. So basically we have a conjecture quasi-exponential security here. And finally, let me steal just a couple of minutes. Yeah, and in a recent work, we also have a version that just uses sparse F2 polynomials without negations, which also is proven to have sub-exponential security against many kinds of attacks. The final thing I want to conclude the talk with is a fairly recent line of candidate pseudo-random functions, both weak and strong in the class ACC0, which has kind of mod 6 gates or alternation between different moduli. And the basic idea is we think of the input as being over F2, apply a secret F2 linear mapping defined by the key, then view the 0, 1 outputs as element of Z3 and apply some linear operation mod 3, say addition. Okay, so we conjectured this to have exponential security. So far it withstood analysis, so there's been several experienced cryptanalysts that tried to break it, so far with no success. It has applications, in learning, including the direct applications that are written here, but perhaps interestingly, this class of functions has some alternate forms. For instance, these functions can be computed by sparse Z3 polynomials or with 3 branching programs. And if you look at the sparse Z3 polynomial representation, it basically tells us that under our conjecture, you get full exponential hardness of learning sparse Z3 polynomials, but under an input distribution, which is kind of weird. The inputs are uniform over 0, 1, 1 to the n. If you think about it, you understand why 0 is not allowed. But this is contrasted with sparse Z2 polynomials, which can only be 2 to the square root n, hard to learn. Okay, and finally, I want to say that, this is motivated by the fact that linear operations are for free in many advanced crypto primitives, including secure computation. So we only pay for the switching from 2 to 3, which can be made very cheap. So Ryan Williams calls ACC annoying complexity class. So to cryptographers, it may actually be a better acronym, awesome complexity class. And I want to say that we recently pushed it in a very practical direction, proposing other implementations of crypto primitives by swapping mod 2 and mod 3. And this even can be used to build the practical post-quantum signatures that improve over some NIST finalists. So, these kinds of simplicity can be very relevant to practice. And finally, really finally, sorry for running out of time. So we can also get strong PRF candidates here, and the idea is just to have a similar to add another level of alternation. So we start by expanding the input using a public mod 3 mapping. Then we take the result mod 2 and we apply a secret mod 2 mapping defined by the key. And finally, we apply compressive public mod 3 mapping. This is conjectured to be exponentially secure. If you believe this conjecture, it gives you a natural proof barrier for ACC0, which the complexity community was on the fence about. And if we instantiate this with the kind of linear size mapping I described before in the hash function, then we get a somewhat dubious, but still a legit candidate for asymptotically optimal PRF. Okay, so it's open to break it or prove K-wise independence, which is challenging. Okay, so the final candidate is just inner product of input and key mod 6 rounded. So it's learning with rounding mod 6. This is some form of deterministic version of LPN. If you change 6 to 5 or 7, it's broken in polynomial time. 6, we don't know how to break it. We conjecture it to be 2 to the order of n over log n secure. Okay, so conclusion, simple hard to learn functions are useful in cryptography in every sense you can imagine. There's still many gaps in our understanding, much more dark matter to be explored. This is an actual, satellite photo. It's really, we understand very little. Introducing new assumptions can help responsibly based on evidence when called for, critical for progress, and we need much more brain power invested in analysis. And finally, it's a joint mission of several communities, even inside cryptography, crypto analysts and theoretical cryptographers. And it's really of interest also to computational learning, complexity theory, algorithms, and other domains. So thank you, and really sorry for running out of time.
First, thank you very much, Yuval. At the interest of time, I would say because of the reception that maybe if Yuval can stay for a few minutes on Zoom, and maybe people can join to ask a question.
Sure, yeah, and as I said, I'll be around on Thursday,
and of course,
Friday, and I'm happy to talk to people.
Yeah, so he will be in person also Thursday and Friday. Yeah. Thank you very much.
Okay, so enjoy the reception and